Hello, everyone.
Hello, ma'am.
Good evening, ma'am.
Yeah, good evening. This is your week 8 solve with us session. So, in this week, you mainly have to study about moment generating functions and central limit theorem. Okay. Have you all gone through the lectures?
No, ma'am.
Okay.
No,
Yes,
ma'am.
ma'am.
I'm not gone.
Yes, ma'am.
Okay, so the very first thing is moment generating function. So, anyone would like to tell me the formula of it? How do we define it?
Mx lambda is equal to e raised to my lambda x.
Okay, so this is in short is called as MGF. Okay, so suppose we have a random variable x. Okay, so it is denoted and given as so it is denoted as mx lambda. Okay, and it is defined as the expectation of this function e to the power lambda x. Okay, so this is how we define this moment generating function. Okay, later we will see why this function is called moment generating function. Okay. Okay, so if suppose if x is a discrete random variable, okay, x is a discrete random variable, and you have to find expectation of gx. Then what is the formula? How do we calculate it? If you have to find expectation of gx, and gx is some function of x, okay, and x is discrete random variable,
So
then we define it as summation of
gx
gx multiplied by
probability.
the corresponding probability, right? This is how we generally define the expectation of some function of random variable x, right? Now we will write it for this mgf function. Okay, so again, suppose if x is a discrete random variable, okay, with pmf, suppose fx, okay, and suppose x takes values, okay, so it is taking values x1, x2 up to xn. Okay, so these are the values taken by x. Now mx lambda is defined as expectation of e to the power lambda x. Okay, this is how we define mgf. Now this is what this e to the power lambda x is actually the function of x, right?
Yes, ma'am.
Yes or no? Okay, so now just apply this formula, okay, here. Okay, so here we know that this is some function and x is taking values x1, x2 up to xn. Okay, so I can write it in this form, that e to the power lambda x1, and then we have to multiply it with the corresponding probability. Okay, suppose it is fx x1. Okay, then the next will be e to the power
Lambda
lambda
x
x2.
fx
Okay,
x2.
and the, yeah, fx x2. Okay, similarly, we can write it up to n terms. So this will be fx x3 e to the power lambda x3, and then it will go up to n. Okay, so this is how we can expand this MGF function. Okay, so this is for a discrete random variable. Okay, if x is a discrete random variable, then we can add it. We can add the different terms for x1, x2 up to xn. Okay, if it is a continuous random variable, okay, if x is a continuous random variable, with PDF. Okay, so x is a continuous random variable, so it will have PDF, right? Suppose PDF fx, then we can write it like this, that mx lambda. Okay, so in general we define it as that expectation of e to the power lambda x. Okay, now if you have to find this expectation, okay, this expectation term, but x is a continuous random variable, so how can we write it? So this formula we wrote for the discrete random variable. If you have to write this thing for continuous random variable, then how will you write? What should I write here? Okay, first of all, this is what e to the power lambda x. Okay, now you have to write the expectation of this function where x is a continuous random variable. Okay, so it will be the integration of this function, okay, multiplied by the PDF into dx, right? And here this integration, the limit will be of x. Is this correct?
Yes, ma'am.
Yes, ma'am.
Simply you just have to find the expectation of this function. Okay, let's suppose for an instance you can consider that gx is equal to e to the power lambda x. Okay, then what we write, this is gx, okay, and this is the probability density function of x. Okay, this is just PDF. Okay, okay, now let's see why this function is called moment generating function. Okay, so we will expand it in a different way. Let's see. So y moment generating function. Okay, so first of all, again, the formula is mx lambda. This is equal to expectation of e to the power lambda x. Okay, now this is exponential function. Okay, so if you remember the expansion of e to the power x, do you all know this expansion e to the power x?
1
This is what, 1, yeah,
plus
1 plus x,
n factorial divided by n square by 2 factorial, like that.
yeah, it goes like this up to infinite, right? So now the same formula, okay, the same expansion we will apply for this function. Okay, so here in place of x we have lambda x. Okay, so now expand it. So this will be expectation. In the bracket we will expand this function. Okay, so it will be 1 plus lambda x, right?
By x.
Then lambda, yeah, lambda x is square divided by 2 factorial. Okay, then it will be lambda x whole cube divided by 3 factorial, and it will go like this. Okay, now we will apply this expectation to all the terms given here. Okay, so what is the value of expectation of 1?
Ma'am, I had a doubt.
What is the expectation of 1?
1.
Yeah, it will be 1 because 1 is a constant value. Okay, so expectation will also be the same constant value.
Ma'am, I have a doubt
Next,
in this
we
form.
have yeah, yes.
In this e power x, e power lambda, what is that, ma'am? The written in red.
Okay, so this is the expansion. You must have studied this formula in mathematics. E to the power x. So this is the expansion of e to the power x. Okay, so that we can write as 1. Then we have plus x square by factorial 2. Then the next term will be
We will find the
x
value of
cube.
e to the power something by this formula.
Yes, we will expand this formula and then we will see why this function is called moment generating function. Okay, I will expand it for few more terms and then you will see. Okay.
Okay, ma'am.
Yeah, just wait for a minute and it will come. Okay, so by using this expansion, we have expanded this term, e to the power lambda x. Okay, so expectation of 1 is 1, then we have expectation of lambda x. Okay, so lambda is some constant, so that will come out of it. Okay, so it will be lambda times expectation of x, right? Then we have this term lambda x whole square divided by 2 factorial. So tell me what will be the expected value of it? This lambda is some constant here. Okay. How can I write it? Simply it will be lambda square divided by 2 factorial and expectation of x square. Right? Yes or no?
Yes, ma'am.
Okay. Then the next term will be lambda cube divided by 3 factorial. Okay. And then
E of x cube.
yes, it will be expectation of x cube. Okay. Similarly, we can write the other terms as well. Now we have to see here that we are getting these terms: expectation of x, expectation of x square, expectation of x cube. Okay, and if you write the other terms as well, it will be expectation of x to the power 4, expectation of x to the power 5, like this. Okay, so these terms are actually the moments. Okay, so this expectation of x, this is called first moment. Okay, the expectation of x square, it is second moment, and this expectation of x cube, this is third moment. Okay, so these moments are not in your syllabus in very detail, but let's have a rough idea what are these moments. Okay, so moments actually helps you to understand the distribution of some variable. Okay, so what
Excuse me,
is
ma'am.
moment? Yes.
Sorry, ma'am. I got late 20 minutes. Can you please tell what is going on in the class?
Yeah, this is week 8 solve with the session. So we are discussing the topic moment generating function.
Okay, how many topics have discussed right now? Can you please tell?
We have just started with this topic only.
Okay, thank you so much, ma'am, and sorry for interruption.
Okay, so moment, basically we have two types of moments: raw moments and central moments. Okay, we have raw moments and we have central moments. You don't need to worry about these moment things much, but let's have a quick understanding about it. Okay, so raw moment is defined as, so it is written as this, mu and dash. Okay, and it is defined as expectation of x power n. Okay, so if I put this value of n as 1, okay, so mu and dash will give you expectation of x. Okay, and this expectation of x is nothing but mean. Okay, similarly you can write mu2 dash, so that will be expectation of x square. Okay, you just have to put the value of n and then you will get first moment, second moment, and third moment, like this. Okay, similarly how central moments are defined. So the formula for central moment is, so we write it as this mu n, and this is defined as expectation of x minus x bar and whole power n. Okay, so this is the key difference between raw moments and central moments. Okay, So here we have to subtract the mean, and here you can consider this term as expectation of x minus 0 whole power n. Okay, so that will actually be expectation of x to the power n. Okay, and here in central moments we have to subtract the mean of the variable. Okay, so here you can see if I write second moment, okay, second central moment, so that will be expectation of x minus x bar whole power 2. Now can you tell me what is this term?
Variance.
Yeah, this is actually variance. Okay, if you expand it you will get x. Okay, you don't need to expand it here. This is actually variance of x. Okay, if you want you can open the square term, put the expectation to each term, you will solve it, you will get it is equal to variance of x.
But for variance, we need to do a summation, right?
Yeah, you will open this square bracket. Okay, you will get x square x bar square minus 2 times x into x bar. Okay, and you have to solve this term, and then you will get it equal to variance of x. Okay, it will be expectation of x square minus expectation of x whole square, which is x bar whole square. Okay,
Okay.
you can try it on your own. Okay, so this is how we define the moments. Okay, so these moments you can see will these moments helps you to understand about the variable. Okay, so that's what you are getting in this function. We are getting the values of expectation of x, expectation of x square, and the other values, expectation of x cube and expectation of x power 4. Okay, so you can see that in this function you are getting these moments actually. Okay, so that's why this function is called moment generating function.
So here, ma'am, the
Okay, is
second,
this thing clear to everyone?
ma'am, here lambda square to factorial e of x square. Is that variance here in this moment?
No, expectation of x square is not the moment. Sorry, it's not the variance. Okay, if you remember the formula of variance,
Yeah,
okay, that
e
is
of x square minus e
expectation
of
of x,
nothing. Yeah, whole square.
okay, minus expectation of x whole square. Okay, so variance of x and expectation of x square, these two are different things.
So
Okay,
those moments are not variance mean. We can say e of x, but e of x square cannot be considered as variance, right?
sorry, your voice is not proper.
Okay, that okay, ma'am.
Okay, so see, this expectation of x square will not give you the variance, but you can use these two terms, expectation of x and expectation of x square, to get the variance. Okay,
Okay,
you
ma'am.
can use this. Yeah, you can use the formula, and then you will know the value of variance.
Ma'am, central movement of order 1 will be 0, no?
Sorry.
Central movement of order 1, and if you put n is equal to 1,
Yes,
it will be
that
0.
will be 0. Yeah, it is 0.
Okay, ma'am. Thank you.
Yeah. Okay, so now you have to recognize some pattern in this equation. Okay, so you can see that in the very first term is 1. Okay, so this is 1. Then in the next term you are getting lambda. Okay, in the next term you are getting lambda square divided by 2 factorial. Then you are getting lambda cube divided by 3 factorial. Okay, so you can see, I will write one line here. So you can see that coefficient of lambda to the power k divided by k factorial. Okay, so this is actually kth moment. Now you can vary the value of k here. Okay, so when you put value of k as 1, okay, Okay, when k is 1, just put k is 1, then you will get it as lambda. Okay, so what is the coefficient of lambda in this equation? In this one?
Ex expected value, ex square, ex cube are the coefficients.
It'll be 1, no?
No, I am asking about the coefficient of lambda in this part, in this equation.
Ma'am, EX. It will be EX.
Ex.
Yeah, it is expectation of x only. Okay, so expectation of x is the kth moment. So what was k here? K was equal to 1. Okay, so when you put the value of k equals to 1, you got lambda, and the coefficient of lambda is expectation of x. Okay, so you can say that the first moment is expectation of x. Okay, similarly, if you put this k is equals to 2. Okay, if you put k equals to 2, you will get lambda square divided by 2 factorial. Now, what is the coefficient of lambda square divided by 2 factorial?
Expectation of
This
x
term,
square.
expectation of x square. Okay, so this expectation of x square is second moment. Okay, similarly, you can vary the value of k and you will get the value of kth moment. Okay, so
So
whenever you are asked to find
the moment is only the coefficient, right? It's not the entire lambda square by 2 factorial. No.
No.
It's
Yeah,
just
it's only the coefficient term.
Okay.
Okay, coefficient of lambda power k divided by k factorial. Okay, this entire, not only lambda. Okay, you have to consider this k factorial term as well. Okay, so coefficient of this lambda to the power k divided by k factorial will give you the kth moment. Okay, don't worry, we'll solve some question and then you will understand how you have to use this equation in finding out the moments. Okay, so is this thing clear up to this point? Anyone have any doubt?
Just the whole point of all this,
Yeah, in the starting I told you that this function is giving you moments. Okay, and why moments? So moments, you can that these moments actually helps you understand about the variable x, about the behavior of it. Okay, or you can say the distribution of x. Okay, so that will actually give you these mean and the variance, you can see. Okay, and you will get these values also, expectation of x4, x to the power 4, and the other terms. Okay, so mainly we use this mean and variance. Okay, so that will help you understand about the behavior of the variable x.
All right, ma'am.
Ma'am, what is lambda actually?
Lambda is some constant value here. Okay, so till now we studied about the MGF of one random variable. Okay, now we'll see the moment generating function of sum of independent random variables. Okay, so and there is one more thing. The moment generating function for normal distribution. Okay, I will write it here. So if you have a variable x which is following normal distribution, okay, with parameters 0, sigma square. Okay, 0 is the mean and sigma square is the variance. Okay, then the moment generating function of it is equal to e to the power lambda square sigma square divided by 2. Okay, so this is the moment generating function for normal distribution. Okay, if you want you can derive it, or you can you don't worry about the entire derivation of it. You should remember this formula. Okay, it will help you in solving the problems. Okay, and if suppose you have a variable x which is following normal distribution with parameter mu sigma square. Okay, then the original formula is actually mx lambda. It is e to the power mu lambda plus half sigma square lambda square. Okay, so this is the MGF for for a variable which is following normal distribution. Okay, so in the numericals you will be using this formula. So it's good to remember it. Okay. Okay, now you can see that you should know the value of mu and sigma. By just putting the value of these two things, you will get the MGF function. Okay. Okay, now we will see the moment generating function for independent random variables. Okay, so suppose you have two random variables x1 comma x2, okay, which are IID according to some distribution x. Okay, now we are defining another variable y, which is the summation of x1 and x2. Okay, and now you have to find the MGF of y. So it will be my lambda. Okay, again you can see we have two variables x1 and x2 which are IID, okay, which are independent and identically distributed to some distribution x according to x. Okay, and then we are taking the summation of these two variables, which is represented as y here. Okay, so okay, first of all, what we can write here according to the formula that we studied in the starting.
E of x raised to lambda into x1 plus x2.
Okay, that is fine. So first of all, we can write expectation of e to the power lambda y, right? The very simple formula. And then we can put the value of y. Okay, so that will be expectation of e to the power lambda, and here it will be x1 plus x2. Okay, and now we will do some calculation. So we can write it as expectation of e to the power lambda x1. Okay, and it will be plus lambda x2. Okay, then we can write it as e to the power lambda x1 into lambda x2. Okay, is that correct? Till this point, anyone has any doubt?
No,
Okay, I
ma'am.
just use,
No.
yeah. So by using the property of independence, we can write expectation of e to the power lambda x1, okay, into e to the power expectation of e to the power lambda x2. Now, what is this first term and what is this second term?
Movement generating function for x1 and x2.
Yeah, so the first term is the MGF of x1. Okay, so we can write it as mx1 lambda. Okay, and the second term is mx2 lambda. Okay, and on the left hand side we have my lambda. Okay, so now here you can see that the MGF of y is actually the product of MGF of x1 and x2. Is that clear? Okay, so we can conclude that MGF of sum of IID random variables, okay, it is the product of their individual MGS. Okay, and you can extend it for more than two variables as well. Okay, you just have to multiply the MGF of MGFs of all the independent random variables. Okay. Okay, is that clear to everyone?
Yeah. So, ma'am.
Yes, ma'am.
Again, just to understand why we are taking the MGF is so that we can find out the mean and the variance and all that just from one equation, right? Is that the point?
Yes, yes.
That's
Yes.
the point, right? Yeah. So
Yeah, that's
Ma'am,
why
can
we
you
use movement.
scroll down the screen so that I can take screenshot?
so ma'am, so what exactly is lambda? I mean, I remember someone else also asking the same question. I mean, is lambda just
Lambda
supposed
is
to be?
some, lambda is some constant value.
Okay. So what's the significance of that constant value? I mean, why are we writing my of lambda? I mean,
See, this is like generally we define this function.
okay.
Okay, and this is the way of writing this function.
Okay.
Okay, so like in if you have studied CDF and PDF, okay, so each thing has some notations, right? Similarly, MGF also has some notation and some formula of it.
Okay.
Okay, so it is the way of defining it.
Okay.
Ma'am, could you go to normal distribution, the formula you wrote? Ma'am,
Yes.
it is written m of x of lambda. Ma'am, where in the right hand side of the equation, where has x gone? Actually, x is not present in the right hand side of the equation. So where has x gone, ma'am?
Okay, here.
Here, ma'am.
Okay, you don't need to worry about why x is not here. If you solve it, you will see that this is the term you are left with. Okay, if you solve the entire thing, entire derivation of it, this term you will get. Okay.
Oh, okay, fine.
Okay, at this point of time, you don't need to worry about the derivation of the MGF of normal distribution. Okay. Okay, next we will study about the centralized random variable. Okay, so what is centralized random variable? So first of all, suppose you have some random variable x. Okay, so suppose it is taking some values x1, x2 up to xn. Okay, and suppose it has some mean. It has some mean which is equal to mu. Okay, now to make this random variable centralized, okay, centralized x. Okay, what you have to do, you have to subtract the mean from each value. Okay, so the first value was x1, so you have to do x1 minus mu. Next you have x2, so we have to do x2 minus mu. Okay, so actually we have to subtract the mean from all the values taken by x. Okay, so this is how we can centralize some random variable. Okay, and when you centralize the random variable, the mean of the random variable, okay, mean of the centralized random variable becomes 0. Okay, mean of centralized x. Okay, so if you make the random variable centralized, the mean will be 0. Okay, so make like centralizing the random variable helps you in some computation. Okay, and in the machine learning courses you will see that it helps you to reduce the multicollinearity. Okay, so that's why we use the centralizing thing. Okay, you can centralize the random variable just by subtracting the mean of the variable. Okay, and further it also helps you in some computation. Okay, it will be easier for you to compare the things. Okay, because the mean is centralized to 0. Okay, so comparing the things from 0 is easier than comparing it from the other values, right? You can easily see the differences and the other things. Okay, is this thing clear to everyone?
Yes, ma'am.
Yes,
Sure,
no.
ma'am.
Yes, ma'am.
Okay, next we have the most important central limit theorem. Okay, so anybody has studied this theorem in lectures or somewhere? In short, it is called CLT. Anyone would like to explain? What is CLT?
Ma'am, I remember the formula only. At
Okay.
that time.
Okay, explain what is the formula?
Suppose we are given a sample x1, x2, dash, 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 xn. If it is IID for independent random variable, then its expected value would be 0 and the variance would be sigma square.
Actually, we are bringing it to normal distribution, 0, 1.
Yeah, so the key idea behind the central limit theorem is, suppose you have some population and it is following some distribution. Okay, so regardless of the distribution of the population, the distribution of the sample mean, okay, sample mean will always follow normal distribution. Okay, so it actually helps you again calculating the probabilities. Okay, so your main population may be following some other distribution. Okay, or maybe some non-standard distribution which we don't know. Okay, some distribution we have studied, like Poisson distribution, exponential, binomial. Okay, these things we know, but maybe the population is following some distribution. Okay, which maybe these Poisson, exponential, or maybe some other distribution which we don't know. Okay, so regardless of the distribution of the population, the sample mean, if you take a large sample, okay, if you are taking a large sample, then the sample mean will follow normal distribution. Okay, so normal distribution already we have that table. Like for normal distribution we have so many things, okay, which helps us to calculate the probability, right? We already have that standard normal table, and we already studied the symmetricity property, and we have so many things studied about the normal distribution, right? That actually helps us to calculate the probabilities. Okay, so that is the key idea behind using the central limit theorem. Okay, so uh, it makes the probability calculation easy. Okay, now let's see the mathematical things of CLT. So this is, suppose you have x1 up to xn, x1, x2 up to xn, which are some IID variables. Okay, they are IID and distributed according to some distribution x. The expectation is, suppose, 0. Okay, and the variance is sigma square. Okay, now we have that if y is some variable which is defined as x1 plus x2 plus xn divided by square root of n. Okay, then if you calculate the mgf function of this y, okay, so that will be tending to e to the power lambda square sigma square divided by 2. Okay, now just look at this term carefully. What is this?
Normal
Yeah,
MJ.
this is the
MGF
mgf
normal
of
distribution.
normal distribution. Okay, so this is the mgf of normal 0 comma sigma square. Okay, so that was e to the power lambda square sigma square by 2. Okay, so here we can conclude that y is set to converge in distribution to normal 0 comma sigma square. Okay, now the main thing we have to see that how we can use this CLT in probability calculation. Okay, so Okay, so how we have to do this thing? So suppose you have variables x1, x2 up to xn. Okay, which are IID. Okay, IID variables. Okay, and the mean of these variables. Okay, expectation of xi. Expectation of xi is equals to mu. And variance of x or variance of xi, this is equal to sigma square. Okay, now we are defining a variable y, which is the sum of these independent random variables x1, x2 up to xn. Okay, now we say if you subtract the mean, okay, so what will be the mean of y? We will calculate it here. Okay, so y is actually summation of all these variables x1, x2 up to xn. Okay, and for all these variables the mean is mu. Okay, so it will be n times mu. Is this clear to everyone?
Ma'am,
You have to
just
add mu n times.
excuse me, ma'am.
Yes.
Ma'am, y minus at last of this page. Okay, my mistake. Sorry.
Yeah. Okay, first tell me, is this thing clear? Expectation of y?
Yes.
Ma'am, please
Okay,
explain this again.
now
Expectation of y, ma'am. This how it is coming as n into mu.
okay. Okay, this thing is clear. Expectation of y is equals to expectation of x1 plus
Yes, ma'am.
x2 up to xn.
Yes, ma'am.
This you can write it as expectation of x1 plus expectation of x2 up to expectation of xn. Okay, now you just have to add all the values. You just put mu. All are having mean as mu, right? So it will be mu plus mu n times, right? Because we have n random variables. So you have to add mu n times. Okay, so it will
Ma'am,
become ultimately n mu, n
ma'am,
times mu.
we also subtracted something from y also, no? To make the mean 0.
No. We are not doing that centralization here.
Okay. I thought y
Okay,
minus.
just okay. Okay, we will do that. Just understand the expectation of y and variance of y first.
Yes, ma'am.
Is this
Understood.
thing clear?
Yes, ma'am.
Expectation of y. Okay.
Yes.
Then we will calculate variance of y. So what will be the variance of y?
E of x squared minus expectation of x the whole expectation of y the whole square.
Yeah, so it will be okay. So if you want to so it will actually be variance of all these terms, summation of all these. Okay, so it will become n times sigma square. Okay, so this will be the variance of y. Is this clear to everyone? Anyone having any doubt?
Is this we are taking for population or sample, ma'am?
What?
Are we taking it for population or sample here? Like mu is for sample or population we are calculating this?
Mu is the mean of these variables x1, x2 up to xn. Okay, and y is the summation of these x1, x2 up to xn.
Okay.
Okay, now the main thing is that y is some variable, okay, which is defined like this: summation of independent random variables. Okay, now what we have to do, if you subtract the mean of y, okay, so mean of y is what? N mu. Okay, and then we have to subtract the standard deviation. Okay, so what will be the standard deviation of y? If variance of y is n sigma square,
Under
then
root
what will
n.
be the standard deviation?
Under root n.
under root n sigma.
It will be root n sigma. Okay. So this entire will follow normal distribution with parameters 0, 1, or we can say it will follow standard normal distribution. Okay, so this concept we have to use in solving the problems. Okay, so what we have to do, so we have to subtract the mean and divide by the standard deviation. Okay, then this y, so y sometimes it can be the summation of the independent random variables, or you may also get the sample mean. Okay, so if you are giving the sample mean, then it will be x1 plus x2 plus xn divided by n. Okay, so don't worry that we will solve in the example and you will see how to use this thing. Okay, so the main idea is that you have to subtract the mean and divide by the standard deviation, and it will follow standard normal distribution. Okay, this is the main thing about central limit theorem.
I mean, ma'am, I never understood why this root n. What's the even previously when you added all the x1, x2s and everything and divided it by root n. I mean, I understand dividing it by
Okay,
n, but why root n?
see, okay, if the variance of y is equals to n sigma square, okay, if you have to find the standard deviation of y, so it will be square root of the variance, and variance
Yes.
is n sigma square. Okay,
Yes.
so this is how it will become root n sigma.
Okay.
Now is that clear?
Yes, ma'am.
Okay, yeah, so we have to divide by standard deviation. That's why we have to take under root of n.
Okay, ma'am. Thanks.
Okay.
What is
Okay,
that?
so
Excuse me, ma'am. Can you hear me?
yes.
Yeah. What is that y minus n mu by root of n sigma? Is that the normal distribution from like centralized normal distribution?
This quantity, okay, this quantity will follow standard normal distribution.
If
Okay,
you want to
so for
convert
making,
any, like if you want to convert any normal distribution to the standard normal distribution, we use this formula.
yes, that's what we do. Okay,
It can be any distribution, right, ma'am? Not necessarily to be normal distribution, right?
this quantity,
Yeah,
this will approximately be normal distribution,
yeah. This
standard
formula
normal
we can
distribution.
use to convert any distribution to normal 0, 1, right?
Yes. So here you can see that these x1, x2 up to xn, okay, they might follow any of the, like, any distribution they can follow.
Yeah, that's what.
Okay, that's what a CLT does. Okay, that's how it is helpful for us. Okay, so population may follow any of the distribution. Okay, but if you take a large sample, okay, so then the sample mean follows normal distribution. Okay, and to make it standard normal, we have to do this thing. Okay, so you previously we saw that it was following normal distribution, but it was not standard normal. Okay, if you do this thing, like you subtract the mean, divide by the standard deviation, it will convert to follow standard normal distribution. Okay. Okay, now let's solve the problems, then it will be more clear. Okay, so first we will solve the questions of MGF, and then we will solve the problem for CLT.
Ma'am, y will follow the normal distribution, and y minus lambda mu divided by under root sigma will follow the standard normal.
See, here we don't need to worry about the distribution of y. Okay, so this thing will follow normal distribution. Okay, but if you make this like if you subtract the mean, divide by the standard deviation, okay, that will follow standard normal distribution.
Okay.
But here these x1, x2 may follow any distribution that we don't know.
But there are some will follow the normal distribution.
Yeah, there are some tend to follow normal distribution.
When
Okay,
number of
some
samples
or
are,
the
number of samples are very less.
the sample size is large.
Okay.
If the sample size is large, not less.
Okay.
Okay, the sample should be large. Okay, so let's solve the first problem. If you have a variable x which is following uniform 1, 2, 3, then find the MGF of centralized x. So try it on your own, then I will solve it. So the question is, we are given the variable x with its distribution, and we have to find the MGF of centralized x. Okay, so centralized x, which means what we have to do here first?
First, we need
We need to find expected value normally.
Yes, to make it centralized x, we have to subtract the mean. Okay, so we will calculate the mean here.
Centralized x means the whose mean expected values are 0.
Yeah, mean of the centralized x will be 0. Okay, not the mean of x will be 0.
So isn't the mean 2?
Yes.
Yeah, it will be 3 plus 1 divided by 2, which will be 2. Okay, so now what will be the values for centralized x? Okay, so you have to subtract 2 for from each value. Okay, so it will be 1 minus 2, then 2 minus 2, and then 3 minus 2. Okay, so it will be minus 1, 0, and 1. Okay, is this clear to everyone?
ma'am, here mean of x, we will add 3 plus 2 plus 1 by 3, right? Or 3 plus 1.
Yeah, for uniform distribution, we have the expected value a plus b by 2.
Ma'am, it is continuous uniform or it is discrete uniform?
I think it is
This is
It is discrete,
this is
ma'am.
discrete. Yeah, it's discrete.
Ma'am, for discrete, it is 1 by 3, no?
1 by 3 is the probability.
True.
The mean will be 1 plus 2 plus 3 by 2, 3, right? Then it will
Yeah.
be 2 again.
Yes.
Yeah.
Expected value.
Okay. Yeah. So the probability for each term will be 1 by 3. Okay. And here also, if you make it centralized, okay, the probabilities will still be the same. Okay. So probability for minus 1, that will be 1 by 3. Probability for 0, that is also 1 by 3. And probability for 1, this is also 1 by 3. Okay, is this clear to everyone? Okay, so now you have to find the MGF of centralized x. Okay, so we got the centralized x. We have to find the MGF of it. So tell me, how will you calculate it?
Fx
1 by 3
to the
into
power
raised to
minus lambda plus
minus lambda plus 1 by 3 into e raised to plus lambda plus 1 by 3.
Yeah, so let's go back to the original formula that we studied earlier. So you can see this formula. Okay, when x was discrete random variable, okay, it was taking some values with some probability. So what we did, so it was e to the power lambda x1 and then the corresponding probability. Okay, so basically you have to put the values of x, okay, values taken by x, and you have to multiply with the probabilities. Okay, so this is how you can get the MGF of centralized x. So Here you can see that centralized x taking value -1, so it will be e to the power lambda into -1, so it would be e to the power minus lambda multiplied by probability 1/3. Okay, then the next term is e to the power lambda into 0, and the probability is 1/3. Next we have e to the power lambda into 1 and probability 1/3. Okay, so it is simply e to the power minus lambda plus 1 plus e to the power lambda divided by 3. Okay, is this question clear to everyone? Anyone has any doubt?
Ma'am, which formula you applied for this? Can you explain a bit?
Okay, so I was explaining this only that if you have x as a discrete random variable, okay, so the original formula is expectation of e to the power lambda x, right?
Yes,
And if
ma'am.
you have to find the expectation of some function of random variable x, okay,
Yeah, ma'am, got it. Thank you.
hello, am I audible
Am I
now?
audible now?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay, so I was discussing this formula. So if you have to find expectation of gx, is this formula correct?
Yes.
I'm sorry, ma'am. I'm a little lost, but where did GX come from?
Gx is some function of x.
Okay. Are we still in that uniform 1, 2, 3 problem?
Yes, yes.
Okay.
So
Okay, someone
GFS
was
is
asking
basically
how
the
did we.
MGF. Ma'am is
Okay, this is
GFS.
the general. See, this is the general thing I'm asking. You must have studied it in week 5, I guess, week 5 or week 6. So if you have to find the expectation of
Yes, ma'am.
of
Yeah,
some
it
function
makes,
of random
yeah.
variable x.
Yes,
How do
yes.
we find that? Okay, and here I am taking that x is taking values x1, x2, and x3 only. So this is what I will write. Is that correct? Yes, no?
Yes, ma'am.
Okay, now I am saying that x is taking these values x1, x2, x3 with probability 1 by 3. Okay, so what will be this? It will be gx1 into 1 by 3 plus gx2 into 1 by 3 plus gx3 into 1 by 3. Okay, now this gx, so gx is the function of some random variable x. Okay, now this function is defined as e to the power lambda x. Okay, now you have to put the value of gx. Okay, so when x is taking value x1, what will be this function? It will be e to the power lambda x1, right, multiplied by 1 by 3, plus it will be e to the power lambda x2 1 by 3, e to the power lambda x3 1 by 3. Now is that clear how this formula comes? Okay, now in this particular question, this x1, x2, and x3, okay, the values of x is 1, 2, and 3. That's what we have put here. Okay, e to the power lambda into -1, e to the power lambda into 0, and e to the power lambda into 1. Now is this thing clear to everyone? Someone was asking about this, how I wrote this thing. Now is this clear?
Yes, ma'am.
Okay, and this e to the power lambda x, this is the mgf of x. So that's what we are taking this function. Okay, this is mx lambda. Okay, this is the mgf function. So we have to take e to the power lambda x, expectation of this function. Okay, so now you can use this formula for any discrete distribution. Okay, now try solving this question. So here x is following Bernoulli distribution with parameter 0.3. And here also we have to find the MGF of centralized version of x. So now try solving this question. So tell me what values are taken by x here, and what are the probabilities?
0 and 1.
1 are the
0 and 1.
values, and for 1 it is 0.3.
1 is 0.3.
Okay, so x is following Bernoulli, so it will take two values, 0 and 1. For 1,
0.
what will be the probability?
0.3.
0.3.
0.3. Okay, for 0 it will be 0.7. Okay, and what is the mean here?
0.5.
0.3.
Okay, so yeah, okay, yeah. So yeah, so it will be 0.3. Okay, what is the expected value of x here? So it is equal to p. Right?
Okay.
Okay, that's what we have to take. Now we have to make this variable centralized. So centralized x. Okay, so we have to subtract 0.3. So 0 minus 0.3, okay, and then 1 minus 0.3. Okay, so this will become minus 0.3 comma 0.7. Is that correct?
Yes.
Okay,
Yes,
and
yes.
what are the probabilities for these values?
For first one it is 0.7 and the second it is 0.3.
Yeah, okay. So now we got the values for centralized x and the probabilities as well. So now simply we have to write the MGF function. Now tell me the MGF function for it.
Your voice is not clear.
0.7 e raised to minus 0.3 lambda plus
Yes, then
0.3, 0.7 into, right?
yes, and then
0.3 into e raised to
e to the power
0 lambda. Sorry, 0.7 lambda.
Okay, so this will be the MGF of centralized X. Is that
Ma'am,
clear to
so
everyone
I'm
now?
just trying to understand the concept of the centralized X thing. I mean, so in centralized, shouldn't the mean be 0?
Yes, mean of centralized X will be 0.
Okay, so in this case, is it 0? You've made it like minus 0.3 and then 0.7, right? I understood how we got that, but is mean 0 in this particular case?
It is 0 actually,
Yeah, it is 0.
because
Yes,
minus
yes. I just calculated. Yes, we get a 0. Thank you.
Okay.
Thank you, ma'am. Thank you, everybody.
Okay, now is that clear to everyone how we calculate the MGF?
Yes, ma'am.
Okay, then move on to the next question. So here we have x1, x2 up to xn, b10, xn, b IIT random variables with common moment generating function mx lambda. Find the MGF of x bar, where x bar is like this is the mean of 10 random variables. So what is the moment generating function of x bar in terms of mx lambda? Okay, so first of all, x bar is x1 plus x2 plus x10 divided by 10. Okay, so it is actually the mean of 10 random variables. Okay, so we have to find MGF of x bar. So we have to find mx bar lambda. Okay, so by using the formula, I can write it will be expected value of e to the power lambda into x bar. Is that correct up to this point?
Yes, ma'am.
Yes, ma'am.
Okay, now what we can do?
You can expand X bar.
Yes. So we can just put the value of x bar here. So it will be x1 plus x2 up to x10 divided by 10. Okay. Now we can write it as e to the power lambda. Okay. Into lambda, e to the power lambda x2 divided by 10. Right? We can write like this.
Yes,
Is
ma'am.
that clear to everyone? Okay. Okay. Now we can write these terms. Okay. They all are IID. We can write it like this e to the power lambda x1 divided by 10. Okay, then expectation of we can write expectation of e to the power lambda x2 divided by 10. Okay, similarly we can write up to x10. Okay, now there is one thing, you can write it as a note. Okay, if you have mxt, or okay, we are taking lambda here, so I'll write lambda. Okay, so this is what we were studying up to this point. Okay, so this is mx lambda. If I multiply with some constant here in x, okay, suppose I am multiplying with c. So now it is mx c lambda. So the value of this thing is equal to mx into mx and c lambda. Okay, these two terms are same. Okay, so if you are multiplying with some constant here, Okay, so that will come here with the multiplication of lambda. Okay, so by using this thing, we can write, so this term will be mx1, okay, and lambda by 10. Now just think about it, compare it with this formula. Just tell me you understand it or not. Okay, here you can take the value of C as 1 by 10. Okay, this is the first term only, okay, not the entire term. Okay, does that make sense to you?
Yes, ma'am.
Okay, so by using that formula, we can write it like this. This is x10. Okay. Now, since all these x1, x2 up to xn are IID, okay, so they are IID, which means like the value of all these terms will be same, right? X1, x2, x10 all are IID, so these values will be same. So I can write it as m x lambda by 10 and whole power
10.
10. Okay. Why I have written x? You can see that it is like we are taking that it is the moment generating function of these variable is mx lambda. Okay, so that's why we can write it mx lambda. Okay, we can remove that x1, x2, and they are distributed according to the x. So we can write it like this, and the whole power will be 10. Okay, we have 10 different variables here. Okay, so this will be the final answer. Now you can match with the given options. Okay, so option number D is correct here. Okay. Is this question clear to everyone?
Yes, ma'am.
Yes, ma'am.
Okay, then should we move on to the next question? Okay, so try solving this one. So let x1, x2 up to x3 following IIDX, and this x is uniform minus 1 comma 1. Okay, which means that all these random variable, all the three random variable are following uniform distribution minus 1 comma 1. Now we are defining a random variable y, which is the summation of these three. So find the distribution of y. Okay, so here we have to find the distribution of y. Okay, so by using the MGF only, we will find the distribution of y. Okay, so first of all, so here y is defined as x1 plus x2 plus x3. First of all, we will calculate the MGF of y. Okay, so how can we find that? Simply, it will be expectation of e to the power lambda y, right? Now we will just put and the same concept we will use here as well. This is x1 plus x2 plus x3. Okay, and then it will be e to the power lambda x1 multiplied by e to the power lambda x2. Okay, and then we can write it like this. Okay. Okay, and the what is the first term?
MGF of X.
Yeah, MGF of x1. Okay, and then the next is MGF of x2. Okay, now we know that all these three x1, x2, x3 are distributed according to x. Okay, so we can write this is mx lambda and whole power
Q.
yeah. Okay, So now our objective is to find the mx lambda, value of mx lambda. Okay, which means we have to find the mgf of x. Okay. So tell me what will be the value of mx lambda if this is the distribution of x. So what will be the probabilities for these two values, -1 and 1?
Half and half.
1 by
Yeah, it will be 1 by 2 and 1 by 2. Okay, because it is a uniform distribution. Okay, so now we can write this value. So what will be mx lambda? So values are -1 and +1.
Lambda plus e to the power minus lambda by 2.
Yeah, e to the power minus lambda plus e to the power lambda divided by 2. Okay. So which implies that the value of my lambda, okay, that will be e to the power minus lambda plus e to the power lambda divided by 2 and whole cube. Okay. Now just open this cube term. Okay, use this formula a plus b whole cube, which is equal to a cube plus b cube plus 3a square b plus 3ab square. Just use this formula and open this term. And tell me what will be the value of m by lambda. Okay, you can write 1 by 8 out of the bracket and then you can apply the formula. Okay, so the first term will be cube of e to the power minus lambda. Okay, so it will be e to the power minus 3 lambda. Okay, then it will be e to the power 3 lambda. Then it will be 3 times a square b. So it will be minus e to the power minus lambda. And then e to the power lambda. Okay. So this will be the final term. Okay. So now we have to work in a reverse method. Okay. So earlier we were calculating the MGF if we were given the distribution of x. Okay. Distribution of random variable is given and we were calculating the MGF function. Now we have to work in the reverse method. So you can see that if you had these two values, if you had these two values -1 and +1, and the probabilities were 1 by 2 and 1 by 2. Okay, so we wrote the MGF like this. Okay, e to the power minus lambda, and we multiplied with 1 by 2. Okay, the next value was +1, so it was e to the power lambda into +1 divided by 2. Okay, now just look at this term and tell me what are the values taken by x and what are the corresponding probabilities. Values taken by y, not x, sorry.
The values
Okay,
would
so
be
basically
Then
you have
values
to
are
see the
C
coefficient of e to the power lambda.
-3, 3, 1 and -1.
Yeah, it will be -3. Okay, here it is -3. Then we have +3. Okay, and then we have -1 and we have +1. Okay, I will arrange it. I will write it proper way. Okay, so -3. Then we have -1. We have +1 and we have +3. Right? These are values. Now tell me what are the these values.
1 by
What is the probability?
3 by 8.
1 by 8,
Yeah, it
3
is
by 8,
1 by 8.
1 by 8,
Yes.
3 by 8. And for 1 by 3 by 8, then 1 by 8.
Okay, so you just have to see the coefficient of the power, coefficient of exponential term. Okay. Now is this question clear to everyone? Okay. Okay, so if you are given the MGF function, then you can find the distribution of x as well. And if you are given the distribution of x, you can find the MGF of x. Okay, x or any variable. Okay, it's not like always x, it can be any variable. Okay, is that clear to everyone? Then we
Ma'am,
will
can you
solve
just
the
zoom
next
out so that I can take a screenshot? Thank you, ma'am.
Okay, anything else? In the last question? Okay. Okay, so this is a question for CLT. So here let x1, x2 up to x100, okay, be the independent and identically distributed random variables, each with expected value 3 and variance 9. Approximate the probability x1 plus x2 plus x100. It is greater than 100, okay, using the central limit theorem. Write your answer in terms of fz, the CDF of standard normal. Okay. So how will you solve this question? So first of all, we are given in the question that x1, x2 up to x100. Okay. They are IID. Okay. They are IID variables. Okay. And then we are given the expected value of x. Okay. Which is mu, which is 3. Also, we are given the variance of these xi's. Okay. Which is sigma square, which is 9. Okay, now the question is to find the value of probability x1 plus x2 up to x100. Okay, so the summation of these 100 variables is greater than 100. Okay, this probability we have to calculate. We have to approximate this probability by using the CLT.
Is the
So the
summation
same.
what was y once upon a time? What we had written as y? Is that what the summation would be in this case?
Yes, yes.
In the formula, what we had calculated as y is.
Yeah, it was that summation of the variables. Okay, so you can consider it as y or any other variable. Okay, it's your choice. So this is our question. Okay, so let's suppose
Ma'am, please show the
x1
question
plus.
again.
Okay, I'll show.
Okay, ma'am.
Okay, so now let's suppose that these x1 plus x2 plus x100. Okay, suppose I am representing it as s100. Okay, you can write it as y also, or you can take any variable of your choice. Okay, suppose it is s100. Now using CLT, okay, using CLT, I can write that this s100, okay, minus what we have to subtract to make it follow standard normal distribution.
Mean.
Yeah, we have to subtract the expected value of this
N
variable as
u
100.
N mu. Okay.
Okay. See, don't just mug up the values, okay? Because it's not always n mu or not always root n sigma. Okay, it depends on what
Okay,
is
ma'am.
the variable here. Okay, yeah, like how we are defining this as 100. Okay, sometimes it will be the summation of variable, or sometimes it might be the mean directly. Okay, so you
Okay,
just
ma'am.
understand what is the key concept. So you have to subtract this mean, okay, or you can say the expected value, and you have to divide by the standard deviation of this variable s100 here. Okay, then it will follow standard normal distribution. Okay, normal 0 comma 1. Okay, so this is the thing we have to use. Now we have defined what is the S100. So here we need to calculate the value of expectation of S100. Okay, so we will calculate this thing here. So this is x1 plus x2 plus x100. Okay, so we can write it. Okay, now these values are given to us in the question. What is this? What is the value of expectation of x2?
3.
3.
3.
3. Okay, it is 3. So all these values are 3 only.
So 100 into 3, right?
Okay.
300.
Yeah, so it will be 100 into 3. Okay, which is 300. Yeah. Okay. Similarly, we have to calculate standard deviation. So for standard deviation, we will calculate the variance first. Okay. So it is variance of x1 plus x2 up to x100. Okay, and since they all are independent of each other, okay, so we can write it as variance of x1 plus variance of x2 up to variance of x100. Okay, so variance is given as 9. Okay, so it will be 100 times 9. Is that correct? Okay,
Yes,
so this will be equal to 900. Okay, so standard deviation of S100, that will be equal to square root of
30.
900. Okay, yeah. Okay, so now we have to calculate the probability that x1 plus x2 up to x100. Okay, this is greater than 100. Okay, this is something we have to approximate. Okay, now this thing, okay, the summation we wrote it as S100. So the value of S100 is greater than 100. This probability we have to approximate. Okay. Now here we will use CLT. So according to CLT, we can write that S100 minus expectation of S100. So what was the expectation of S100? 300.
300.
Okay.
300.
We will subtract the expected value, divide by the standard deviation. It was root of 900. Okay. Same thing we will have to do on the right hand side as well. Okay, to balance the equation. Okay. Now this term, we can write it as z. Okay. Okay, this is the standard notation we use for standard normal variable, right? So we can write it as z. So z is greater than this value. Just calculate this value. What is this?
Minus
2 by 3.
6.67.
This will be minus 200 divided by 30. So it will be minus 20 by 30.
Minus
Okay?
6.6.
Okay, this is the thing. Now in the question it was written that we have to write the answer in terms of fz. What is fz? Standard CDF of standard normal variable. Okay, so we have to convert it in terms of CDF fz. So this thing I can write 1 minus probability that z is less than or equal to minus 20 by 3. Is that correct?
Yes.
Yes, ma'am.
I can write it like this or not? Okay, it is just
Yes,
a
ma'am.
complementary event of it. Okay, so we can write it like this. And this term, this is what? This is fz at point minus 20 by 3. Okay, is that correct?
Yes.
So this is your answer. Okay, so now you can see that in the last term, we have written the value in terms of CDF of standard normal variable. Okay, so this is your answer. Okay, so maybe in the exam, the value of this term will be given, so you can put the value. Okay, in this particular question, it was given that you have to write the answer in FZ, in terms of FZ. Okay. So is that question clear to everyone?
Yes, ma'am.
Okay. Okay, now let's see the next question. Okay, so the question
Ma'am,
is suppose.
excuse me, ma'am.
Hmm. Yes.
Ma'am, after this question, can you first please explain the theory of alpha, beta, and gamma distribution? Because only 25 minutes are left.
Sorry, theory of what? Your voice is not coming properly to me.
Alpha, beta, and gamma distribution.
Okay. Okay, so those are actually some distributions and their mean, variance, and the other properties are given to you. Okay, those distributions are not in very
Yes, ma'am.
detail, so I did not discuss that. Okay, so just some introduction part is there.
Ma'am, please discuss that.
Okay.
It is quite confusing even after watching the lecture.
Okay. Okay, let's solve these questions and then we'll discuss that. Okay, so the question is suppose
Okay.
speed of vehicle on a particular road are normally distributed with mean 25 mph and standard deviation of 3 mph. So find the probability that the mean speed of x bar of 30 randomly selected vehicles is between 24 and 27. Okay. So let's suppose x is some variable, okay, which is representing the speed of vehicle. Okay, so now in the question it is given that x is following normal distribution. Okay, the mean is 25 and the standard deviation is 3. So variance will be 3 square. Okay, so this is given in the question. Now next it is given that we have to find the probability that the mean speed x bar of 30 randomly selected vehicles. So we can see that the sample size here is 30. Is that correct?
Yes, ma'am.
Okay, sample size is 30. So we have to find the probability that this x bar, okay, this mean speed is between 24 and 27. Okay, this is something we have to calculate. Okay, so first of all, whenever the question is given, we have to write it in this mathematical format. Okay, some theory will be given to you and you have to convert it like this. Okay, you should be able to understand this. Okay, that what we have to find actually in mathematical terms. Okay, now you can just use CLT here. So what is x bar? If you have to define x bar is actually x1 plus x2, okay, plus x30 divided by 30. Okay, I will write in general first. So it will be xn divided by n. Okay. So now if you have to find the expected value of x bar, so how will you find it? So you just put the value of x bar. So it is x1 plus x2 up to xn, okay, divided by n. So it will be 1 upon n, then expected value of x1 up to expected value of xn, okay, then it is 1 upon n, and you have to add mu n times, right? Because we have n sample sizes n, so it will be mu time n times mu. So this will become mu. Okay, so we can say that the expected value of x bar here is mu. Okay, similarly we can find variance of x bar. Okay, so that will be 1 upon n square. Okay, and then variance of x1 up to variance of xn. Is that a thing clear to everyone? If you have any doubt, you can ask now. Okay, so this is 1 upon n square, and what will be the value of this term? What will be the value of variance of x?
n into sigma square.
Yeah, n into sigma square. Okay, and finally it will be sigma square divided by n. Okay. Okay, so this is the variance for x bar. If you have to write standard deviation of x bar, this will be sigma divided by root n. Okay. Now let's go back to the main question. It was to find the value of that x bar lying between 24 to 27. Okay, this is something we have to calculate. Okay, so here also what we have to do, we have to subtract the mean of x bar, okay, and divide by the standard deviation of x bar. Okay, so this will follow standard normal distribution. Is that thing clear to everyone?
Yes, ma'am.
Okay, so the same thing we have to do here. Okay, now 24 minus what is the value of expectation of x bar? So this is mu. Okay, and in the question the value of mu is given. Okay, so mu, okay, so this is the value of mu. Okay, and this is the value of sigma square. So mu is 25. Okay, so it will be 25, and then we have to divide by the standard deviation of x bar. So this mu is 25. Standard deviation of x bar is sigma divided by root n. So what is the value of sigma here?
20. Next second.
3.
3. Okay, value of standard value of sigma. Okay, it is given as 3, and the sample size n is 30. So it will be 3 divided by under root 30. Okay, so this will be 3 divided by root 30. Same thing you have to do this side as well. Just calculate these two values. Okay, and this value is actually z. Okay, this is standard normal variable. Now tell me these two values.
-1 by under root 0.3.
Tell me the values in the decimal. What did you say? In the options,
Under root 0.3.
we have to find the values in these terms, like in this way. So this will become minus 1.82. Okay, similarly, what will be the value of this term? 27 minus 25 divided by 3 by root 30. This will be 3.65. Is that correct? Everyone is getting this value?
Yes.
Okay. Okay. So Z is lying between minus 1.82 to 3.65. Okay. Now here you have to use some properties of normal distribution. Okay. By using that, we can write that it is equal to Fz 3.65. Okay. Minus Fz minus 1.82. Is that clear to everyone?
Yes, ma'am.
Okay. These are the properties of normal distributions. You must have studied it. So this is your final answer. Now let's check which option is matching with this answer. 3.65 minus 1.82. So option number A is correct. Okay. Now is this question clear to everyone?
Ma'am, we have taken
Yes,
the
ma'am.
events to be IDDD because it is mentioned randomly selected. Right?
Yeah, in the question in itself it is given. Okay.
Ma'am, a little request, if you could just zoom out. I mean, I would like to screenshot it. Thank you, ma'am.
Yeah, this is the next part. Okay. Okay, yeah. The next question is, what is the fourth moment of normal 0,9 distribution? So x is suppose some random variable which is following normal distribution. Okay, with parameters 0,9. Okay, so we have to calculate the fourth moment here. So according to the formula of MGF, mx lambda, okay, this is equal to what? Expectation of e to the power lambda x. Okay, and in the starting of the session, we wrote it like that it is 1 plus lambda x. Okay, if you open the expansion of this term, e to the power lambda x, you can write it like this. Okay, whole square divided by 2 factorial, then whole cube of this term divided by 3 factorial, and so on. Okay, already we have discussed this thing. Okay, now next we can write it as 1 plus lambda expectation of x plus lambda square divided by 2 factorial and expectation of x square. Okay, like this we can proceed it. Okay, now so this is the general thing. Okay, for about this is the general thing about MGF. Now for normal distribution we saw the formula of MGF. Okay, so we know that the MGF of some random variable x which follows normal distribution with parameters 0 comma sigma square. Okay, so this was e to the power lambda square sigma square divided by 2.
Yeah.
Okay, so this was the formula for MGF of normal distribution. Okay, with this parameter 0 comma sigma square. Now, so this is lambda square sigma square by 2. Okay, now if I open this expansion, okay, suppose this is some term. Okay, you just have to apply the expansion of e to the power x. Just consider it as one term and apply the exponential expansion formula. Okay, that we applied here as well. Okay, same thing we will use. So by using that, we can write that it is 1 plus lambda square sigma square by 2. Okay, then square of this term lambda square sigma square by 2 square divided by 2 factorial. Okay, then it will be lambda square sigma square by 2 whole cube of this term divided by 3 factorial. Okay, in this way we can expand this thing. Okay, we can expand it. Now in the question it is given that what is the value of fourth moment. Okay, so we have to find fourth moment here. And the thing we already studied, okay, we already discussed that how can we find the kth moment. Okay, so what will be the fourth moment here? Fourth moment is actually the coefficient of
Lambda.
What will be the
lambda raised to k divided by k factorial.
Yeah, so here we have to find fourth moment. So it will be lambda raised to power 4 divided by 4 factorial. Okay, so we just have to look at this formula and we have to find the coefficient of lambda power 4 divided by 4 factorial. Okay, so look at this thing carefully. You can observe that here you will get lambda power 4, right? Here we are getting lambda square only. Here it will be lambda square whole square. So that will give you lambda power 4, right? In this term, you will get lambda power 6. Okay. This is how you can compare it. Okay. So we only need to worry about the third term, this term. Okay. So now this term is actually lambda square sigma square by 2 whole square divided by 2 factorial. Okay. Now from this term, you have to find the coefficient of lambda power 4 divided by 4 factorial. So you just have to make it like that. Okay. So if I open the square, it will be lambda square, lambda power 4. It will be lambda power 4 sigma power 4 divided by 4 into 2 factorial. Is that correct?
Yes, ma'am.
Okay. Now we have to make it lambda power 4 divided by 4 factorial. So lambda power 4 we already have in this part. Okay. 4 factorial is not, we are not having it directly in this part. So to make it 4 factorial, what can we do?
We can
Multiply and divide with 3.
Divide by 4.
Yeah, we can multiply. Yeah, we can divide by 4 factorial as well, and then you can see the remaining things. Okay, it's your choice. You just have to do some mathematical thing, just some calculation, and you will get it. Okay. So it will be lambda power 4 sigma power 4. Okay. And it will be 3. And then in the denominator, it will become 4 factorial. Is that correct? Now we will write 4 lambda power 4 divided by 4 factorial separately. The remaining things are 3 sigma power 4. Okay. Now you can easily see that the coefficient of lambda power 4 divided by 4 factorial is 3 into sigma power 4. Is that correct?
Yes, ma'am.
Okay. So we can see here that coefficient of lambda power 4 divided by 4 factorial, this is equals to 3 sigma power 4. And the value of sigma is given in the question. Okay. So we are given the distribution normal 0, 9. So what is the value of sigma here?
3.
It is 3. 3. So it is 3. So it will be 3 whole power 4. So what will be the final value? 3 power 5? 243. Okay. So now we can write that the fourth moment, okay, fourth moment of normal 0, 9 will be 243. Okay, value of fourth moment. Okay, is that clear to everyone? Okay, so this is how you just have to compare with this equation. Okay, so we already know that this is the MGF function for normal distribution. You just have to expand it. Okay, and you can find the coefficient of lambda power k divided by k factorial. Okay.
Ma'am, this distribution does not have
Excuse
a
me, ma'am.
third moment.
Excuse me, ma'am.
Yes. Yeah, so you can observe one thing, that in this equation we don't have odd powers of lambda.
Yes, ma'am.
Okay, we only have even powers of lambda. Okay, so we can say that all those moments, okay, we can see that first moment, third moment, so those will be 0. Okay, all the odd moments will be 0.
Here, after 1 only, we will consider as moment, right, ma'am? Sigma square, lambda square by 2 is the first moment, right? The constant will not be considered as a moment, right?
Here you can take it as lambda power 0.
Yeah. Do we consider it as a moment? No, right? It's a constant, right?
Yeah, this is a constant value.
So we
Okay, we'll
count
start
Zero
with first
moment.
moment.
So count we will start from the second, right?
No, it's not like that. In this particular case, it is going like this. Okay,
Oh,
we can always have 0th moment, first moment, second moment, and third moment like this. It depends on the distribution, what is the value of those moments. Okay, so in this particular, like normal distribution, the value of odd moments, okay, is 0.
so here if we
Okay,
take 1 as the first moment, then 1 is the value, right?
no, this one will give you the value of 0th moment. Okay, the value of first moment is 0. We don't have lambda power 1 here. Okay,
Okay, okay,
lambda
okay.
power 1 is missing from this equation. So we
Okay.
can see yeah, we can say that lambda power 1, the coefficient of it is 0,
Okay.
or lambda power 3, the coefficient of it is 0.
So
That's
it
why this
starts
term
from
is
0, you mean
not
to say
missing.
0, 1, 0, 2, 4, like that in this distribution. Otherwise, normally it starts from 0, right?
What starts with 0?
Like as you said, lambda raised to 0 is the 1, right? So we will be
Yeah.
considering the moments like that. Lambda raised to 0, lambda raised to 1, like that, right?
Yes. Okay, now is that clear to everyone? Okay, then solve the next question. Okay, yeah. So in a telecom system, each data file consists of 500 bits. Due to noise, each data bit received may have an error with probability 0.1. Okay, it is assumed that bit error occurs independently. So the first is, suppose y represents the total number of bits without an error in a certain data file. So which of the following is true? So what is the distribution of y? Just read the statement, read the question again, and see what will be the distribution of y. Just think about it.
C, I guess.
It's binomial, right?
Yes.
Yeah, it will be binomial.
Binomial, because there are n number of bits.
Yeah, so it's correct that y will be following binomial distribution. Okay, and we are given total. Each data file consists of 500 bits. So in total we have 500. Okay, and y is representing the total number of bits without error. Okay, and in the question we are given the probability of error. Okay, so without error will be the 1 minus this probability. So 1
0.
minus 0.1, which will be 0.9. Okay, so option number C will be correct here. Okay, is this clear to everyone? Yes, no?
Yes, ma'am.
Yes, ma'am.
Okay. Now the second part is, using central limit theorem, find the approximate probability that there are more than 53 errors in a certain data file. Okay. So first of all, you have to convert it in mathematical terms, and you have to see what exactly you have to calculate and what things you are given to calculate that probability. Okay. So you can assume that you just have to take some variable. Suppose a. Okay, x and y are already have been used. Y is already used, so I am taking, suppose a is some variable. Okay, suppose a is some variable. Suppose ai. Okay, so it takes value 1 when there is a error in a data bit. and it takes value 0 when there is no error. Okay. So what distribution AI will be following?
Bernoulli?
Yeah, it will follow Bernoulli distribution. And what will be the probability? You can go back to the main question
0.9.
and see what will be
0.1.
okay.
Sorry,
So it will be 0.1. Okay, because if it have an error, okay, then the probability is 0.1. Okay, so just okay, why are we taking like this? You can see that we are interested in approximate the probability. There are more than 53 errors, so we are actually interested in the error part, okay, not in the without error. Okay, so that's how we are taking this variable, that it is taking value 1 there is an error in the data bit. Okay, and the probability for error is 0.1. Okay, so this AI will be following Bernoulli distribution with with parameter 0.1. Okay, now this okay, now we can take that x is some other variable which is representing the total number of error. Okay, so this x will actually be equal to the a1 plus a2 up to a500. Okay, why 500? Because it was already given in the question. Okay, that each data file consists of 500 bits. Okay, and each bit can have an error or may not have an error. Okay, this is the thing. Okay, now does this thing make sense to you? Okay, now according to the question, we have to find the probability that this x is greater than 53. This is something we have to calculate. Okay, just read the question again. We have to find approximate probability that there are more than 53 errors in certain data file. Okay, so this a1 a2 up to a500, so they can take either value 1 or value 0. Okay, so if there is an error, this AI will be taking value 1. If there is no error, then it will be 0. Okay, so like this we will be having some values 1 0 0 1 1 0 like this. Okay, so this is how it should be 53. It should be greater than 53. Okay, some bits will be having an error or some bits will not be having error. Okay, so in total there should be more than 53 errors. Okay, this probability we have to approximate. Now is this thing clear to everyone? Just read the question again and just read this thing what I have written. Is that clear to everyone? Someone wants to ask some question? You can ask.
Ma'am, I have a question regarding the statistics to extra activities scoring logic. So, ma'am, can I ask now, because it's almost the end and maths class has already started, I think.
No, let's finish these things first. Okay, you can ask your doubts regarding extra activity in the TA sessions. Okay.
Okay, ma'am. Okay.
Okay, so because this is something you have to make some efforts on. Okay.
Okay, ma'am. No problem. No, actually, I have a question regarding I have a confusion regarding the grading, not the extra activities, only the grading. Okay, so I'll ask in the TA session.
Yeah. Okay. About grading also, the instructions are given. Just read them carefully.
The formula is a bit confusing.
Okay, you can. Okay, you can discuss that in TA sessions. Okay.
Okay, ma'am.
Okay, so is this question clear to everyone till this point? Then I will move forward. If it's not clear up to this point, then it will be confusing later. If you have any doubt, then I will repeat the question again. Just say yes, no, something.
Yes, ma'am, you can move, continue.
Okay. Okay, so we have to find that x is greater than 53. Okay. Again, we have to use that concept of CLT. Okay, we will subtract the mean and we will divide by the standard deviation. Okay, of this variable x. We will convert it into standard normal distribution and we will calculate the probability. Okay. So we have to calculate the expected value of x and variance of x. Okay. Now x is defined as a1 plus a2 up to a500. Okay. So tell me what will be the value of this? Okay,
0.1.
you can
500 itself.
Is it 5?
500 into
yeah.
0.1.
So 500 into 0.1. Okay, because here the value of p is 0.1.
Oh, okay.
Okay.
That's 50,
So
right? Or...
okay, so this will be 50. Yeah. Okay. Similarly, we have to find variance of x. So variance of a1 plus a2 up to a500. So this will also be 500 times. And what is the variance of AI? Variable AI?
45.
P into 1 minus P, it will be 0.09.
1 into 0.9.
Yes, ma'am.
Okay. P to 1 minus P. So this will be equal to 45. Okay. Okay, now we will just do that thing. X minus expectation of x divided by the standard deviation of x greater than 53 minus, what is the value of expectation of x? It is 50. Okay, and root 45. Okay, so this term is probability that z is greater than, just calculate this value.
Divide 3 root 5.
Okay, so this will be probability that z is greater than 1 by root 5. Okay, this we can write it as that 1 minus probability z is less than or equal to 1 upon root 5. Okay, and now we can write it as 1 minus fz of 1 upon root 5. Is this clear up to this point?
Yes, ma'am.
Yes,
And
ma'am.
value is given in the question.
1 minus 0.
It is 0.67. So 1 minus 0.67,
0.33.
0.33. Okay. Is this question clear to everyone?
Yes, ma'am.
Anyone else? Okay. Okay, then this is the last question. Okay. So the question is, let x be a random variable having the gamma distribution with parameters alpha equals to n and beta is equals to 1. Okay. So some hints are given in the question that if x is following gamma with alpha comma beta, okay, so the expectation and variance of the gamma distribution is given. Okay, in the exam also these formulas will be given to you. Okay, then we have to use CLT and these SZ values are given. Find the minimum value of n such that this probability is less than 0.1. Okay. Okay. So first of all, we are given that x is following gamma distribution with parameter alpha is equals to n, okay, and beta is equals to 1, okay. So now we can calculate the value of expectation of x. So expectation of x is alpha by beta. This is alpha by beta. So that will be equal to what? For this x, which is given in the question. Just put the value of alpha and beta. What will be the value of expectation of x? If alpha is n and beta is 1, it will simply be n.
Yeah.
N upon 1, which is n, okay? And alpha upon beta square, variance of x, this will also be n.
Yes.
Okay. Now, probability of mod of x by n minus 1 less than greater than 0.01. It is less than 0.01. So from here we have to find the minimum value of n. Okay. So this term we can write as x minus n upon n. Is that correct? Just take the LCM in both the terms. Okay. You just have to do some calculation and you will find the value of n. Okay. Now this is x minus n divided by n. Now here you can see that both the expectation and variance of, so expectation of x is n, okay, and standard deviation of x, what will be the standard deviation of x?
Root n.
Root n, okay. So in central limit theorem, what we do, we subtract the expected value and divide by the standard deviation of x, standard deviation of that variable. So here we have x. So you can see that in this term, we have subtracted the expected value, okay. And this term is the variance of x, not the standard deviation. So we can write it like this, that x minus n divided by root n into root n. Is that correct? Okay. N we have written as root n into root n. Okay, mathematically it is correct?
Yes, ma'am.
Now I can write it as x minus n divided by root n and greater than this 1 root n and transfer to this side. So this will be 0.01 into n. And this entire is less than 0.01. Is that correct? Anyone has any doubt in this part?
Yes, ma'am. This is
Okay.
Can you
Now
explain again?
0.01 n, ma'am.
Okay. See, okay.
Root
So
n.
n we can write it as
Root n into root n. That I got.
okay. So n we can write it as root n into root n. Okay.
Okay.
Both are equal to each other. Now we just transfer one root n to this. Okay. If it is written x minus a upon b equals to c. So I have written x minus a equals to cb. Okay. Just transfer one root n to this side.
But you have multiplied
write
with
it
n, right?
Okay. We just
n, right?
oh, okay. Sorry. Yeah. It will be root n. Sorry. Yeah. By mistake I wrote this.
Okay.
Okay. Now is this correct? Okay. So it will be root n only. Yeah.
Yeah. Okay.
Okay, now is that correct? So now you can see that x minus n divided by root n. So here you can see that it is the expected value of x. And this is the standard deviation of x. So now this entire has actually become standard normal variable. Is that correct? Okay, we have subtracted the mean divided by the standard deviation of x. So this will become standard normal variable. Okay, now we can write that mod z is greater than 0.01 root n. Up to this point, anyone has any doubt? Is this clear to everyone?
Yes, ma'am.
Yes, ma'am.
Okay, now we just have to find this value. So just visualize it, if I draw it, okay, so we all know that normal distribution has property of symmetricity. Okay, so mod z is greater than 0.01 root n. So suppose this is some point which is 0.01 n, and this is some point minus 0.01 n. Okay, so this shaded region and this shaded region, this is what mod z greater than 0.01 root n. So is this area clear to everyone, or do you need more explanation?
No, ma'am, it's clear.
Anyone else having any doubt in this part?
Ma'am, can you repeat the area part?
Okay. Okay, so let's take some general thing. Okay. Suppose you are given mod z is greater than some constant c. Okay. Now, if you have to visualize, this is the normal graph, and this is some point c. Okay. So mod has two things, positive and negative. If I take positive, okay, so positive will be z greater than c. If I take it as negative, then we have minus z greater than c. Or I can write it as z less than minus c. Is that correct?
Yes, ma'am.
Is that correct or not? Okay. So now you can see that mod z greater than c, it actually consists of two reasons. Z greater than c and z less than minus c. Okay. So if this is some point c, so this will be minus c. Okay. So because of the symmetricity, okay, these two areas will be same. You can see z is greater than c. So z greater than c will be this shaded region. And z less than minus c will be this shaded region. Is that correct?
Yes, ma'am.
Okay, so mod z greater than c, it consists of these two reasons. Okay, and these two reasons will actually be the same because of the symmetricity property. Okay, so now here you can see that this value of c is 0.01 under root n. Okay, this is some constant value. So now I can write it as probability. So, okay, so can I write it like this, that 2 times probability of z greater than c. Okay, z greater than c and z less than minus c, both are same things. So we just have to double one side. So 2 times z greater than c. May I write it like this? Mod z greater than c. What I have written that if you have to find probability mod z greater than c, okay, by using this figure, this diagram, we can write probability that z is greater than c, 2 times of it. Is this thing clear to everyone? Okay, so now just put the value of c according to the question. Okay, so this thing we can write 2 times probability of z greater than 0.01 root n. Is that correct and clear to everyone?
Yes, ma'am.
Okay. Okay, now this thing we can write, this is 2. Okay, and this term probability z greater than this 1 minus probability z less than or equal to 0.01 root n. Okay, both are same. Okay, now we can write this is 1 minus, this is what, cd of standard normal at point 0.01 root n. Now up to this point, is it clear to everyone?
Yes, ma'am.
Okay, now just solve it. So we can transfer this 2 to right hand side. It will be 1 minus fz 0.01 root n. Okay, and less than, it will be 0.005. Okay, when you divide, so 0.01 divided by 2, if you do, then it will be 0.005. Okay, just transfer 2 to right hand side. Now just solve it. Just find the value of fz 0.01 root n. So this we can write as, this will be greater than 1 minus 0.005. So it will be 0.995. Is that correct? Clear to everyone?
Yes, ma'am.
Yes.
Okay. Okay. So we have solved up to this point. Now we need to go back to the question and see what values we are given. So we are given these two values. Okay. So we got this term where probability of 0.001 root n. Okay, this is greater than this one, 0.995. So at the place of, okay, so 0.995 is equal to fz 2.58. Okay, so we are given that fz 2.58. Okay, this is equal to 0.995. Okay, so now fz 0.01 root n greater than, okay, now at the place of 0.995 we can write fz 2.58. Is that correct or not?
Yes, ma'am.
Okay, these two values are equal to each other, so we just replace the values. Okay,
Okay, ma'am.
now we can just compare left hand side and right hand side. Okay, and we can write that 0.01 root n is greater than 2.58. Okay, and here we can write that root n will be greater than 2.58 divided by 0.01. And then if you square both the side, you can write that n is greater than 2.58 divided by 0.01 whole square. Just solve this value. So this we can write n is greater than 258 whole square. Yeah, so this will be n greater than 66564. Is that correct?
Yes, ma'am.
Okay, so this will be the minimum value.
Yeah.
So minimum value will be so n is greater than this values. Okay, so minimum value of n is 66565, right? Because n is greater than, okay, and n is a sample size, so that will always be an integer value. Okay, so minimum it will be the next value to it. Okay, so it will be 66565. Okay, so now from the options we can see option number B is correct. Okay.
Okay.
Is this question clear to everyone?
Yes, ma'am.
Okay, yeah, so this was the last question. If you have any doubt, then you can ask. Anyone has any doubt?
Okay, ma'am.
So only these kind of questions will be asked from gamma and other distributions. By giving the formula, we need to come to the conclusion, right, ma'am?
Yeah, so yeah, see, those kind of questions will not be there most probably in the exam. gamma distribution and those. And if they are asked, that will not be very tough questions. So the information will be given to you in the question.
Okay.
Okay, so these formulas will be given to you. You don't need to mug up those formulas. Okay, so those distributions are just for introduction. Okay.
Okay, thank you.
Okay, if no one has any doubt, then we can end the class.
Ma'am, the recording of this class would be available, right, on the calendar link?
Yes, it will be available.
Thank you, ma'am.
And PDF will be in there in the supplementary contents, right?
Yes, it will be uploaded.
Thank you, ma'am.
Thanks a ton, ma'am.
Yeah, thank you, everyone.